It gives me great pleasure to present the next speaker. Up next is Rhonchi, Associate Professor and Woodruff Faculty Fellow of Georgia Tech. Has a quite impressive bio that I will now read. Dr. Yo is a Woodruff Faculty Fellow, Associate Professor in the Mechanical Engineering and Biomedical Engineering, and the Director of the IEN Center for Human-Centric Interfaces Engineering at Georgia Institute of Technology. His research focuses on the areas of nano microengineering, soft materials, molecular interactions, and biosystems, with an emphasis on nano-membrane bioelectronics. Dr. Yo received his PhD in mechanical engineering at the University of Washington, Seattle. Afterward, he was a postdoctoral research fellow at the University of Illinois at Urbana-Champaign. Dr. Yo has published over 120 peer-reviewed articles, including many in top-quality journals like Nature Materials, Nature Machine Intelligence, Nature Communications, and Science Advances. In addition, Dr. Yo is an IEEE senior member and a recipient of a number of awards, including multiple NIH R01 awards, NIH Trailblazer Young Investigator Award, IEEE Outstanding Engineer Award, Emory School of Medicine Research Award, EMEA Innovation Award, Lucy G. Moses Lectureship Award, Sensors Young Investigator Award, American Heart Association Innovative Project Award, and Outstanding Yonsei Scholar Award. Please welcome Dr. Rhonchi.
All right, thank you for your nice introduction. I didn't know that you will read everything through it, but really appreciate that. It's really first time to hear that. I know everybody's having challenging time after lunch, but I'll try to make you awake, and hopefully I can deliver something regarding my research. And as you see from the title, my talk will be a little bit different from previous speakers. I'm going to focusing more on the devices and systems that I do. And actually today I'm going to talk about my research in terms of developing soft biomedical wearable stethoscope and the embedded machine learning for automated real-time disease diagnosis. All right, before jumping into my research, I want to briefly introduce my research group at Georgia Tech. I don't know whether you know Georgia Tech, but we are in the US Southeast location in the city of Atlanta. And currently my group has multiple people. We have a fantastic group of people who love research, and they are really dedicated to research. So I'm having great time working with them on a daily basis. So currently we have over 30 people in the group. So we have 10 postdocs and 20 plus graduate students. So we work as a team. So we have internal collaboration to develop like new systems and new biomedical solutions to tackle problems from healthcare. So we study like fundamentals of mechanics, materials, machine learning, manufacturing, and system integration and packaging. So based on that, we develop new systems. And as you see from this title, we develop soft biosensors and bioelectronics. And currently we have over 20 projects funded by national agencies and nonprofit foundations and corporates as well. But pretty much all the projects are really targeting to develop new biomedical systems for disease diagnosis, health monitoring, therapeutics, and human-machine interfaces. And here, this slide, I include a few examples that we are currently developing in terms of wearable and implantable devices. And obviously, I only have 19 minutes, so I cannot cover everything. So today, as I briefly mentioned, that I'm going to focusing on the project that you could see here, right there, right? So wearable digital stethoscope. So for those of you who never heard about soft electronics, here I prepare a photo that's basically showing my hand, this hand, wearing two different devices, one on the wrist and the other on the fingers. And I know that a lot of people these days utilize smart wearables, right? Smart watches, rings, and other things. And as you may know that those wearable devices are using rigid electronics. They include rigid sensors and rigid plastic components, and they follow the rigid packaging to make those systems. But they are wearable because it's miniaturized and still utilize soft materials like elastic bands and others to wear them. Those devices are great because they can really give you some information. However, when you think about continuous monitoring and really measuring high quality clinical data that doctors want to see, they have limitations because those rigid sensors are losing their contact, and you're not going to get high quality clinical valued signals when somebody is having any motions or going through showers and activities, anything like that, because of the mismatch between the rigid sensor and soft tissues like human skin. So easily those sensors are losing those contacts. So that's why we are designing this soft material based electronics, which is really following the material and mechanical properties of the human skin in terms of wearables. So as you see from this photo, that device on the fingers have different form factor. Is following the material property of the human skin, and the ultra thin material based device is really lightweight as well, so that it's going to be having great contact and conformal lamination to the skin for high quality data recording continuously. So based on that idea, here we are really designing this electronics. Initially, the top left photo, that's the one that I developed during my postdoc in 2011, which was published in Science. It was great because everybody liked it. And as you see, that it looks great, right? So it has the best capability in terms of wearability because it's ultra thin. It's so thin and so light. So it's like a sticker or a temporary tattoo that you can put on your skin. That's great. However, in terms of clinical standpoint, it cannot really give you something that they want to see in terms of doctor's standpoint because it has limited capability in terms of putting sensors and electronics all together. So we could barely power that device by using inductive coupling, and we cannot really have continuous wireless data transmission from the device because there's no battery and there's nothing like electronic circuits. So by considering those meaningful data recording with patients and other human subjects, we are trying to take advantages from the existing industry and the manufacturers who are developing ICs and electronic chips and others. So that's why we put that something on the x-axis, which is really giving us a chance to develop a new system that can be functional for measuring realistic data with patients. So that's why we created this soft hybrid system that can take both advantages from this wearability and reliability, functionality, and so on. But as you see that the entire form factor is still very small, and the device is still very soft, flexible, and stretchable, so that you can still maintain that quality of contact that we want with the skin, so that eventually you can get really good signals that doctors want to see from the conventional medical devices. Then you may wonder how we can really design those soft hybrid electronics. So here I'm giving you one example where we can change this conventional rigid electronics to a soft one shown on the right-hand side. So there are many different things that you can do, but you can start from changing the material from rigid plastic and rigid metal to soft polymer. And also at the same time, you can reduce the material thickness from really thick material, and now you can go to really thin, ultra thin nanomembrane material. Then we can really reduce the bending stiffness so that this material becomes flexible without mechanical fracture. At the same time, once we have this nanomembrane, then we can make patterns on it, as you see from the bottom right? And then this ultra-thin membrane can be integrated with soft polymer. Then it becomes a composite, soft composite. Then now this composite can handle applied strain and stress without fracturing the important material like metals and semiconductor. So based on that idea, here we are developing many different types of bioelectronic systems, as you can see from here. Today I cannot share everything, but we typically follow the printing-based manufacturing technology so that we could print number of sensors and the multi-layered circuit. And at the end of the day, we just integrate those miniaturized chip components to make this hybrid electronics. Once you have this electronics, then you can do many different things that doctors want to really have. So here, based on these wearables, we are measuring non-invasive signals. I'm not sure whether you heard about this, but we typically measure biopotentials from our targeted heart, like ECG electrocardiogram, and also we can measure brain signals, electroencephalogram from the scalp, and also we can measure other signals like from the eyes and muscles. And at the same time, we can measure respiration, temperature, blood oxygen saturation, and multiple signals in real time. Then once you have that capability with those devices, now we can do ambulatory health monitoring, which is completely wireless, completely portable. So users don't need to be just staying at hospital. They can bring this device to their home so that we can really measure the continuous data and their daily activities with those devices for better healthcare and better health monitoring. Once we have that, then we can do automated disease diagnosis when we machine learning and AI technologies with it. And also we could provide virtual reality and mixed reality-based therapeutics by integrating our sensors with the therapeutic components. And lastly, by using those wearable sensors, we can measure humans' intention, right? From the brain and other muscles and their activities, then we can do this persistent human-machine interfaces. But obviously today I'm going to talk more about this, our recent outcome published last year. So if you're interested in, please look at this paper, as you see from here. Basically here we are developing a new microphone-based wearable stethoscope that can really hear heart and lung sound from users so that you can use those devices for real-time and automated diagnosis of pulmonary disorders. So as you may know that there are many different issues with the lungs, and when you look at the statistics, because of these pulmonary disorders, many people are dying, 1 death every 4 minutes worldwide, and these are typical diseases that we are looking for: asthma, COPD, like chronic obstructive pulmonary disease, and pneumonia and things like that. So many people are suffering because of these disorders. And what doctors do is that they typically use this auscultation to screen those problems. So they just use this stethoscope and listen to the sound, like from lungs or hearts. And as you know, that is the easiest way and the simplest way to hear sound and find out whether there is any problems with this specific patient. However, as you can imagine, these methods are very subjective. Doctors are relying on their experience and also their knowledge. And although, as you see from this diagram, stethoscope is developing as time goes on, so now we see this digital stethoscope instead of just conventional acoustic-based manual. However, still these brand new stethoscopes are depending on clinicians' decisions when it comes to diagnosis. And also, there are a couple of new devices and new technologies coming out in this area. However, these devices still have limitations like motion artifacts, and they cannot really handle noise. And also because of rigidity that I mentioned at the very beginning, they don't have great contact to the skin, so they are not going to get clinically important signals. And at the same time, those brand new stethoscopes are still very bulky and big, right? So in terms of size, so they are not really designed for continuous wear and continuous data recording that doctors want to have. So based on that motivation, we developed this ultra small device, as you see, something that's on my finger, right? It's ultra thin, right? In terms of thickness, it's less than 9 millimeters, and in terms of weight, it's only 7 grams, including everything, like sensors and electronics all together. And it's very soft and flexible. And also, we integrate this with soft bandage, like the medical bandage, as you see, so that it can be easily mounted on the skin directly. So you can put that near the heart on the chest area for listening to heart sound, or you can put this on the back side or side of your body to hear lung sound. And even we can miniaturize system further and further. So now we are working with a lot of pediatric patients in Atlanta, working with children's hospitals, so that you can put this device for their bodies, unlike the conventional ones, for continuous health monitoring from sick babies and kids and so on. When you open this device, as I said, that it includes all the required components to get really nice data and the sound that you want to hear. So as I briefly mentioned, that we use printing technologies to have multi-layered circuit, as you see. And then we integrate miniaturized chip components. And here we use digital MEMS microphone, which is located right there on the right-hand side. And also we integrate the electronic chips. And here we have Bluetooth low energy chip with microcontroller, and also we have a rechargeable lithium polymer battery, which is very small again, but we can use multiple times by just recharging the battery after multiple days, so that we could have this data recording from the heart and lung wirelessly. And these are a few examples where we can get the data by using our app that we developed for Android smartphones and tablets. And more importantly, here we want to have real-time and continuous detection of abnormality, right? So we are trying to help those doctors. And also we want to give freedom to those users so that they don't need to worry about staying in hospital, so that you can bring this device to their home, as I mentioned earlier, right? So what we did was that we integrate those machine learning and AI components here. So we go through this clinical database, and we train our data sets with CNN, convolutional neural network, so that our device can compare the real-time data with those abnormal data sets to find out whether there's any abnormal signal measured by this specific person or not in real time. And if that happens, then the system can automatically alert that results to the clinicians or users for immediate follow-ups. For device performance, people wanted to really have this outcomes, because doctors are always questioning about our capabilities. So we wanted to have that side-to-side comparison between our device and the state-of-the-art digital stethoscope that you can see, which is coming from 3M. As you see, that form factor is completely different, and at the same time, that rigid device is heavy. So to have really nice signal recording, the doctors have to push this stethoscope to the skin, which makes obviously patient uncomfortable. However, it's going to be more problematic when it comes to measuring those sound when somebody's moving, right? So typically, doctors tell you that stand still to measure those data and listen to heart and lung sound. And that's true, because when you see from the bottom graph, if there's any motion, that you are getting those noise. However, for our ultra-thin wearable device, can really get rid of those noise so that you can have continuous data recording, unlike the conventional stethoscope. Even we designed two different types of devices with the same configuration, right? The top one is the soft wearables that we targeted, but at the same time, we designed the same thing with the same components and everything. However, it's rigid, based on rigid platform. And as I mentioned, that once it's rigid, then rigidity can cause problems of conformal contact, and also is very susceptible for motion artifacts. So when you compare those two devices, you see those blue curves. You have huge spikes, and those are noise that you get typically when somebody is moving. When there's any walking or running environment, any activities like that, can really kill the nice signal, so that doctors are listening to those noise. So we wanted to prove that by taking this video, right? So best subject is always my graduate student. So this guy is wearing two devices. The top graph is showing the soft flexible one, and bottom graph is the one with rigid platform. So as you see that when this guy started to walk, you see those distorted peaks. These are noise that you can typically see. But the flexible one is still showing nice hard sound, typically capturing S1 and S2 sounds. And the difference is even bigger when this guy is running, right? So you see a lot of peaks, which are typical noise that you can measure. So based on these wearables, we are clearly measuring the S1 and S2 sound, and we can even measure those data in this digital way, so that we can use them for machine learning. And so left-hand side, which is showing S1 and S2 data that show the heart valve openings and closure. And on the right-hand side, you see where we measure lung sound when we put our device on the back side of the user, so we can clearly measure inhale and exhale sound. And here we are also utilizing this Wavelet denoising algorithm to really suppress the noise and have better thresholding when it comes to signal processing. And there are 4 different types of lung diseases that we are targeting. Far left, you see crackle, and top right, that's rhonchi, and bottom left, that's wheeze, and bottom right, that's stridor. And each graph has 2 different things. Left-hand side, that's our device, SWS. On the right-hand side, that's the 3M device. And as you can easily notice, our device has a lot better signal-to-noise ratio compared to the digital stethoscope, because of the many reasons that I mentioned earlier. And here, this graph shows the spectrogram that we got for targeted patients. So we work with over 20 patients at Emory University in Atlanta, and also we are working with our collaboration partners in South Korea as well, 2 biggest hospitals, one in Yonsei, the other Asan hospitals. So basically, we are trying to gather as many as patients that we want. So we are targeting over 200 patients right now. But at the moment, we work with 20 patients here, having 4 different symptoms. And you can visually see that they have different outcomes like this. And based on our CNN model, we can have this nice classification of those disorders. So when we compare our patients with a normal data set, we can get about 95% of accuracy to distinguish each disorder from others. And also we develop our own algorithm, as I mentioned that, and also the application for iOS and Android. So here, that's something that doctors are looking at, right, with patients when they use these soft wearables. So they are, when they are normal signals and nothing's really happening, but when there's any abnormal signal coming up, then it will really tell you that classification outcome, and also it will tell you whether there is a problem or not, so that doctors can take a look at further. So this video clip is capturing that machine learning demo with one of our wearables. So this guy is wearing the soft stethoscope over the backside of his body. And the little green box, I'm not sure whether you can see that, is really showing the real-time classification. So initially, it's saying normal, and then when this guy simulated something that's not normal, then it's really capturing the abnormality. And because of the ethical issues, I cannot really share the videos with patients, so please understand that. But that's how we design our application, to have real-time data recording, saving, and also detecting those abnormalities, and also classifying those diseases that we want to see. Right, so considering the time, I need to stop here. So today I briefly share something about materials and the systems that we are developing for soft biomedical wearables. And the goal of my research is always trying to help people and advance healthcare through better health monitoring and diagnosis, therapeutics, and machine interfaces. And hopefully next time I will have another chance to share other researches that we are doing in terms of human-machine interfaces and therapeutics. With that, thank you for your attention. I'll be happy to answer any questions.